Okay, so here's the complement principle. So let A be an event and A prime be its complement. Complement sort of means opposite, like total opposite of what that would be. So like if we're talking about cards, like the complement of picking a red card would be a black card. Or the complement of like a rainy day is a day that it doesn't rain. All right. If the probability of A is P of A, then the complement of that is equal to 1 minus P of A. So when you see the word at least or not, usually at least is easier. It means you should probably use the complement principle. Don't have to, but it's usually easier in problems where you see the term at least. For example, if I rolled a die like 10 times, or flipped a coin 10 times, and I want to know the probability of getting at least one head in those 10 flips. To do that, you'd have to find the probability of getting heads once, twice, 3, 4, 5, 6, 7, all the way up to 10 times. Or you could find the probability of flipping tails every time and subtract that from 100%, and that would give you the probability of getting heads at least once. So here's a similar example, just a little simpler. If we flip 2 coins, what's the probability of rolling at least one head? Well, the probability of, if we draw out the sample size, we see you could do tails, tails, heads, tails, tails, heads, or heads, heads. So we could see that the probability of rolling at least one heads would be 3/4. So that'd be like the direct way of doing it. And in this case, where it's only 2 coins, you can kind of do it this way, and it's not that hard. Now the other way to do it would be to find the opposite of at least one head. So the probability of no heads, which would be tails, tails. And there's 1/4 way to do that. So if you take 100% and subtract 1/4, you also get 3/4. And again, in this problem, it's not that hard to do it either way. But when you get into like bigger numbers, bigger sample sizes, you might want to think of using this. So just another way to approach these problems. Okay, here's a deck of cards. They come up a lot in these types of problems. So it's good to know how a deck of cards works. You can always just pull this up on your screen if you ever have a problem that has to do with deck of cards. Just Google deck of cards and a picture like this will come up. So there are 52 cards total. There's 4 different suits. You got spade, that's not a spade. You got clubs, spades, hearts, and diamonds. And then in each suit there's ace, and then 2 through 10, and then jack, king, and queen. Alright, so these are called the face cards because they're the cards that have a face on it. So decks of cards are used in probability for a lot of reasons. Gambling is a form of probability, and there's a lot of overlap between decks of cards and these concepts. So if you want to just soak this in for a minute, you're going to need to know how a deck of card works to do these next few problems. Okay, another important topic that you need to go forward are mutually exclusive events. So those are events that have nothing in common. So if A and B are events in the same sample space, the probability of A and B occurring are given by, so the probability of A plus the probability of B minus the probability that both those things occur. So we'll get into more specific examples, but pretty much if 2 things aren't mutually exclusive, like picking, if you remember the decks of cards on the previous slide, picking like a jack, a face card, let's say, or picking a heart. Since there are jacks of hearts, they're not mutually exclusive. If you pick a jack, you might also pick a jack of hearts, or you might pick a jack that's not a jack of hearts. So if you wanted to find the probability of picking a jack or heart, you would add the probability of picking a jack plus the probability of picking a heart, but then subtract the probability of picking specifically a jack of hearts, because you chose the jack of hearts, you counted it in this probability and in that probability. Alright, but if they are mutually exclusive, like let's say we're rolling a dice, the probability of rolling a 2 and a 3 are mutually exclusive. They can't occur together. It's either one or the other. So the probability of rolling a 2 or a 3 could just be the probability of rolling a 2 plus the probability of rolling a 3, because you can't possibly do them both. Alright, so I kind of said this example here before, but let's say we take a face card and a jack. Alright, so jacks are a subset of face cards. They're not mutually exclusive because there are face cards that are jacks. But the probability of a diamond and a black, all the diamonds are red and all the black cards are black. So those would be mutually exclusive. So it's important to keep that in mind. And if things are mutually exclusive, you add their probabilities together. If they aren't, you add them together and then subtract the overlap, the probability of both those things occurring, not one or the other.